and I changed the title. So hopefully some of you were here yesterday and heard Dan Andrews talk about the Resource Prospector mission. I'm going to have one real brief slide on it. I'm the project scientist for it and also in charge of site characterization and planning. And I'm going to give you a case study where we're looking at a North Pole target. One of the requirements we're fielding right now for the mission is we go to either North or South Pole, and we have to evaluate either against the mission design capabilities. And this list of people is really a sub-list of people who have been working on these products, of course. But I wanted to give them at least some credit here. I'm presenting their work, really, not mine. The Resource Prospector mission is a HEOMD mission out of AES, the Advanced Exploration Systems, to characterize at the human scale, I like to say, resources, in particular volatiles and water, at one of the 2 poles of the moon. And it is in phase A right now, had passed a mission concept review, is moving towards phase B, and we've done a lot of work over the last couple of years driving down risk. This just shows kind of a quick mission summary. It's a 300 kilogram class rover with a variety of instrumentations on it, including a 1 meter drill, near-infrared spectrometer system, radiometer, imagers, a neutron spectrometer, and a gas chromatograph mass spectrometer system. We built a prototype last fiscal year, and that's what's shown here, with led out of JSC. So that's one I think I should say too, is Resource Prospector is a broad collaborative across the United States and potentially internationally, with Taiwan helping us work on the lander. If you want more information on this, be happy to talk to you about it. For the sake of time, we're going to move on. What I have in this slide is a paraphrased set of level 2 measurement requirements for the Resource Prospector mission. Of course, at the level 2, there's about 350 requirements, but I boiled it down to these. It is organized in a usual structure for minimum fold and stretch goals. And the point being here, these really guide the kinds of traverse planning and the activity planning we need to do to demonstrate that the mission closes on the requirements, the level 1 requirements. And just for quick reference here, we always design to the full success first and then try to get the stretch as best we could. Of course, the management says, well, when you check off your minimum success, and we assure them we'll do that too on their way to full success. But we're looking at traversing and making measurements in multiple locations of about at least 1,000 meters separated in radial distance, both subsurface, surface measurements, and acquire, and this is the one that the engineers just hate us for, is acquire from shadowed area. It's driving into permanent shadowed regions and making measurements. So what I'm going to present today is a study case for the crater Erlanger, which is to the southeast of Perry and at the North Pole. Here's a little context map, situated between Perry and Fibiger. And the reason we picked this particular place is because it has a unique hydrogen signature. This is from the Lunar Prospector neutron spectrometer, the epithermal counts. And what you can see here, here's Fibiger here, here's Erlanger, and here's Perry. So one nice thing, of course, these neutron maps still have very low spatial resolution. And it's nice to find kind of an outlier like this associated with PSRs, because it gives you some assurance that there indeed is some specific, unique increases in hydrogen in this area that you can explore. We did look at Fibiger first, and for a variety of reasons, it's difficult. We may go back there. So we're actually now, as you'll see, targeting kind of in between Fibiger and Erlanger in this region. A NAC mosaic of Erlanger showing its general relief. It's actually a really beautiful crater. And for this particular traverse exercise, and this is something part of just a mission planning process, is we need to demonstrate that a North Pole target could meet our requirements within the capabilities of the system. It's easy to sit there and design a blue sky rover with nuclear power source and everything else, but Resource Prospector out of HEO is a cost-capped, cost-constrained mission, and so we have to actually live within very tight constraints, both schedule, monetary, and also capabilities. And I list here the general constraints we use in this study: roving slopes of 15 degrees, drilling slopes of 5, meaning when we drill we should be more level. Again, to keep costs down, it is a solar-powered rover and also uses direct-to-earth communication. And these are really important constraints, as you'll see in a second, when trying to plan a mission. We have limited our shadow operations. We're in full shadow to less than 6 hours. That, of course, sizes batteries and when you have a solar-powered rover. And we have a range of flight rules that are applied here, including battery depth discharge, charge times, etc. And then also a final really, really important constraint is the speed made good. If anyone who sails, that's kind of a nautical term. You love to say that your rover can drive 10 centimeters per second, but once you figure in latency, bandwidth considerations, human decision support, obstacle, everything collapses to an average speed of less than typically 2 centimeters per second. On most mission studies that have shown rover driving duty cycles, robotic rovers are usually sitting still 80 to 90% of the time and only driving the rest of the time. So that's what we figured into this. We have an instrument requirement that we never drive over 10 centimeters per second. That's for the neutron spectrometer. So between steps, we'll be driving no more than 10 centimeters per second, but on average, our speed made good is only a couple centimeters per second. As we do this exercise, we identify with the team areas that have highest priorities, of course, with elevated hydrogen, I just mentioned that, but also looking at things like near-surface water stability temperatures. Are there areas, as Dave Page and Matt Siegler have shown, that very near the surface, water temperatures, or surface temperatures, subsurface temperatures can be cold enough to retain water for very long periods of time. Those are areas of interest. And of course, PSRs. We really want to understand the volatile content in PSRs, but also beyond that, we want to understand the trafficability, the mechanics, the temperatures at scales. This is all at scales we have no access right now to with the data sets. It's scales of meters to tens of meters. So we really need to understand the environment to move forward with the next missions as well. So this is one of the high priority aspects of this mission. Real quick then, as I mentioned, there's a range of instruments on the rover, and these really define how we use them to define a range of traverse activities. And I have them listed here. Prospecting is the general use. It's prospecting. It's driving around and sniffing and looking for volatiles. We use our primary instrument for that is a neutron spectrometer, but we also can look at surface reflectances and temperatures with a near-infrared spectrometer radiometer system. That's where we drive and we're looking, we're sniffing. Then when we find a particular area we want to map in more detail, we do what we call an area of interest mapping. It's basically zigzagging back and forth, filling in areas of key interest of morphological units, etc. Again, using the neutron spectrometer and near-infrared systems. And then when we really want to go nuts, we actually pull out the drill and we drill down to up to a meter, able to take 10 centimeter bites down to a meter. We can do that in what we call a near-surface assay mode, where we use the near-infrared spectrometer system and look at cuttings very quickly. That's a low overhead measurement, meaning it doesn't take a lot of power, doesn't take a lot of time, and when you're racing against the sun, that matters. And we call that an NSA. That's basically the drill and nervous instrument. And then when we really want to analyze something in depth with the GCMS system, we do what's called a volatile analysis, or VA. That's where we grab a sample, put it into an oven, warm it to various degrees of temperatures, and analyze any of the gases that come off of it with the gas chromatograph mass spectrometer. So one of the first steps is we look at basically maps of the Erlanger area, and we look at things like hydrogen. This is total illumination and slopes. And one of the important things that I want to make very clear in this is a good first start, but what we've learned over the year or two is this really can mislead you when you look at static maps like this and say, oh, I've got a lot of maps. So with this, for example, this map shows the total illumination over 6 months. And these yellow areas mean they get about 60-70% sun over a 6-month period in northern summer. Great, we'll put a place there. Well, it's very time dependent, and from hour to hour, that can change radically. And then once you fold COM on top of it, hour to hour, that can change radically because of the topography and the low sun angles. This is a great place to start, but what we found is it is a very insufficient place to start. You need to go, into a dynamic evaluation. And so none of the tools really existed well to do that, or to do that well. So over the year or so, we've developed new tools with colleagues at CMU, here at NASA Ames, both in the technology offices and the exploration offices, to build tools that allow you to look at these traverses in a much more dynamical, interactive way. This runs through, the next series of slides runs through a traverse that uses a tool that will tell you exactly how much time you have or where you can access while maintaining a certain level of margin against calm and sun loss. The engineers care about that. They're not going to let the scientists take the rover right up to a shadow boundary that is only 2 hours away from sunset. They're not going to do that. They've got margins for rover safety. This tool actually tells you what those calm and sun loss margins are. It then allows you to auto-traverse, green saying good, red being bad, but this red you'll see in a second is deliberate, and you can plan in activities, take in all that time, put in the speed, make good, all these constraints, and it can check it against reality. So this is one particular traverse we did at the southern part of Erlanger. I'll walk through these really quick. Basically, what you're going to see is an arrow stepping through this traverse here and the various activities at each of the science stations that we've defined. And what you'll notice is keep an eye on how these colors change here. And this just gives you how dynamic this all is. This is over a 10-day period. And you can see you basically have to chase and follow the sun and calm avenues of connectivity to actually get these missions to beyond 3 or 4 days. And this is true for the North Pole, South Pole, etc. It's very site dependent, very time dependent. And so at the end of all this here, I'm going to get towards the end, we've got a couple runs into PSRs. That's what these red segments mean. So we actually are running into a PSR, taking samples, doing measurements inside, and processing those samples outside. This total mission here ends down towards Fibiger. Fibiger is right down in this area, so we're moving towards the area with higher hydrogen concentrations. We can evaluate this in a timeline fashion like this, and that's what basically this shows. I'm not going to get into the details here, but ultimately, for this particular area, we were able to evaluate a traverse that worked, meaning it met all of our constraints on the rover and within the mission. That was a total of 10 days. It went about 7.5 kilometers. And we had a total of 6 science stations doing at least 12 subsurface samples and surface sampling, of course, all the way continuously. And then I'll just wrap up a little bit with kind of showing that traverse overlaid on top of some maps so you can get a sense of where it is. Here's Erlanger again, and the PSRs are red areas, and you can see we went into this PSR over here and over here. And this just shows the elevation map as we traversed. Finally, here's a water equivalent hydrogen. Yes, low resolution. This is from Lunar Prospector, but that's the nature of it. You can see we go from generally drier to higher hydrogen concentrations towards the southeast. And this is an ice stability depth map Matt Siegler has provided to us, similar to what Dave Page has done. And red areas basically are places that where water is stable, would be stable theoretically, very near the surface. And you can see we delve into each of these places here and here and here, and that's it. That's the intent, it's to sample all through those environments. So, in summary, the planning of a mission with mobility in particular is very unique and has very challenging aspects to it, especially at the poles. Having that low sun angle, the sun's never more than about 8 degrees above any horizon point at any time. The Earth, likewise, is very difficult, very challenging. And that really puts constraints that are variable in time and space. However, the tools we've developed now really are giving us a lot of confidence that these kind of 10-day missions are doable with a relatively simple solar-powered, battery-powered rover system. So you don't need to go with the nuclear power option, for example. There are potentially areas where you can get much longer traverses, where you can actually find areas where you have persistent sun that lasts for maybe several months. You'll always lose COM, and that's one of our conditions, is you can never rove without COM. This is not fully autonomous rover. You could park it there, survive, and then come back and work another day. This rover, again, is not designed to survive the lunar night. So there's a lot of potential there for increasing mission duration, however you like. Ultimately, though, we did not only meet the minimum and full success, but we delved deep into the extended mission requirements we had for Resource Prospector. So that was a success. And of course, we're going to continue to work with this both in an automated and waypoint planning, combining both machine learning algorithms with the human operator and the human sense to actually better plan and coordinate the activities within the mission timeline. And then the next step, of course, is, as Eisenhower once said, every plan, no plan is sufficient, but planning is indispensable. We know as soon as we hit the moon, we're going to have to replan. And how much fun will that be when you've got your sun setting in an hour behind you? And with that, thank you.
Okay, and again, we'll keep moving on. And also, Tony's got to get to the other room a little bit here. So the next talk is by Jeff Pleisha, Seismic Exploration of